This lecture is on equilibrium points, which are important features of dynamical systems. We start with a simple definition and a simple example of an equilibrium point. An equilibrium point represents a stationary condition of a dynamical system. As an example, consider a ball and a surface and assume the ball is initially located at position A. We want to see if A is an equilibrium point. For this system, A is not an equilibrium, as the ball slides down because of the gravitational force. Now let's consider position B. Since there is no sideways force at this point, the ball doesn't move. So B is an equilibrium point for this system, and this system has one equilibrium point. We now consider another simple example. Again, we want to find the equilibrium point, which in this example is a point where the sideways force is zero. This system also has one equilibrium point at position C. If we locate the ball at any other point, it will not stay there and will slide down. In the third example, consider a ball on a flat horizontal surface. Any point on this surface is an equilibrium point because there is no sideways force at any point on this surface. So this system has infinite number of equilibrium points, and the equilibrium points are not isolated from each other. We call them non-isolated equilibrium points. We are now ready to give a rather technical definition of an equilibrium point. Consider a dynamical system x dot equals f of x, where x is an n-dimensional real vector. The state xe is an equilibrium for this system if f of xe equals 0 for all t greater than or equal to the initial time, which is assumed to be 0. There is no difference if the initial time is assumed to be t0 instead of 0, as the dynamical system we consider is time invariant. So to calculate an equilibrium point of a system, we just need to let the derivatives of all state variables be 0 and find the state variables xe that satisfy f of xe equals 0. To learn more about state variables and state space representations, see the video linked below. If a dynamical system has an initial condition x of 0 at an equilibrium point xe, then it will stay at the equilibrium point forever, that is, x of t equals xe for all t greater than or equal to 0. We now consider several examples. In the first example, we consider a nonlinear system in the form of x dot equals x squared minus 4. To find the equilibrium points, we assume x dot is 0 and obtain that x is either minus 2 or 2. So this system has two isolated equilibrium points. In the second example, we consider different systems with different number of equilibrium points to emphasize the fact that a dynamical system, and in particular a nonlinear system, can have 0, 1, or multiple equilibrium points. Let's start with the no equilibrium point case. Consider these two systems and note that x dot is non-zero in both systems. Therefore, they have no equilibrium points. Now consider these two systems and note that x dot equals 2x is a linear system while x dot equals x cubed minus 1 is a nonlinear system. The linear system has one equilibrium at x equals 0. The nonlinear system also has one equilibrium point, which is at x equals 1. In the third case, we study another nonlinear system x dot equals x squared minus 1. To find the equilibrium points, we'll let x dot be 0 and obtain that x squared is 1, and therefore there are two equilibrium points at minus 1 and 1. Finally, we consider the interesting case where a system has infinite number of non-isolated equilibrium points. Consider this system and note that it's a linear system with two state variables x1 and x2. To find the equilibrium points, we'll let x1 dot and x2 dot be 0 and obtain that the product of a 2 by 2 matrix and a two-dimensional vector is 0. Since this system is not full rank, we end up with two equations which are actually the same. So any x1 and x2 that satisfy x1 equals minus 2x2 is an equilibrium point for this system. If we plot the points that satisfy this equation, we see that all points on this line belong to the set of equilibrium points for this linear system. And since the equilibrium points are not isolated from each other, we call them non-isolated equilibrium points. In the third and final example, we consider a mechanical system which has infinite number of isolated equilibrium points. This system is a pendulum with friction, where m is the mass of the bob and L is the length. We assume the rod is rigid and has zero mass, and there is a frictional force resisting the motion which is proportional to the speed of the bob. We denote the coefficient of fraction by k. The dynamical equation of this system is in this form, which is a nonlinear equation as there is a sine function on the right-hand side of the equation. We first rewrite the system model in a state space form and let x1 be theta and x2 be theta dots. Then the state equations are as shown here. To find the equilibrium points, we set x1 dot and x2 dot equal to 0 and solve for x1 and x2, and then obtain that x2 is 0 and x1 is equal to n pi. We know that a pendulum has only two stationary positions, when the bob is hanging straight down and when it's at the topmost position. The equilibrium points are repetitions of these two positions. The pendulum might have full swings and finally rests at one of these two positions. So this system has infinite number of isolated equilibrium points at which theta equals n pi, where n is an integer and theta dot is equal to 0.